Welcome to FYI, the For-Your Innovation podcast. This show offers an intellectual discussion on technologically enabled disruption, because investing in innovation starts with understanding it. To learn more, visit arc-invest.com.
ARC Invest is a registered investment advisor focused on investing in disruptive innovation. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions. It does not constitute, either explicitly or implicitly, any provision of services or products by ARC. All statements made regarding companies or securities are strictly beliefs and points of view held by ARC or podcast guests, and are not endorsements or recommendations by ARC to buy, sell, or hold any security. Clients of ARC Investment Management may maintain positions in the securities discussed in this podcast.
So today we're joined by Khalid, the founder and CEO of Stemloop, a company that is focused currently on using cell-free biosensors, and we'll get into what that is in a minute, to monitor and fortify the water supply around the world. His team has recently been featured in Nature and Forbes magazine. So Khalid, welcome to FYI.
Thank you, Simon, so much for having me. I'm excited to be here.
Yeah, I think a good place to maybe start off before we get into the company and the technology is just learning, first and foremost, a little bit about you, how you came across and got your interest in biology in the first place. So maybe thinking back even before you did your undergraduate studies, was there anything that kind of piqued your interest and forked you down this road of, biology, computation, and kind of the interesting combination of those two things?
Yeah, absolutely. So, I think a large part of the story sort of stems from my father. So my father is a biochemist. He has a PhD in biochemistry, and he's also an inventor. So sort of a fun fact here that he had actually invented the baby gate in the 80s. So prior to his invention, it was just a barrier, right? And my dad had the really sort of straightforward idea here about hey, why don't we just put a gate in the barrier so that adults can pass through, but children sort of remain stuck behind the gate. And there's actually a picture of me as a 2-year-old sort of stuck behind this gate, grabbing the bars, crying, trying to get to the other side. So I was, sort of exposed to biochemistry as well as this idea of hey, if there's a problem that you can solve and, that may require invention, then go out and do that. So I give him a lot of credit for that. I was sort of exposed to biochemistry, and, he actually did some work at home, some invention at home. So we had a laundry room, and adjacent to the laundry room, he had sort of like an electrophoretic chamber, where you're applying voltage, across a solution and migrating DNA. So that, I think, sort of set the framework for my interest in the field of biology and biochemistry very specifically. And then I was always into tech. So, in the 90s, as sort of a preteen teenager, I was spending a lot of time on the internet, pirating a lot of content on the internet and also building websites. So I built, a couple of fan websites and enthusiast websites and things like that. So that, I think, sort of started to drive my interest sort of not only in biochemistry, but also just broadly in technology. And then as a graduate student, I went into graduate school thinking I was going to do plant genetic engineering, but very quickly became exposed to the field of synthetic biology through an exam prompt, actually. And, that sort of led me to where I am today.
Well, you have it's a difficult legacy to live up to with the baby gate. It's quite ubiquitous. I'm picturing you as the little Gerber baby model on that, which I promise I will not use as the thumbnail for the podcast.
No worries.
Anyway. Yeah. So actually, I wanted to maybe ask you because, the past couple of years, I've spoken to so many people who have a different conceptualization of what synthetic biology means to them. And so for the people who might be hearing this phrase for the first time, what would you want to impress upon them to help them kind of get their mind in gear around what it means to do synthetic biology?
Yeah, absolutely. So I think the term, biotech is something that people are familiar with, right? And it's this application of biology as a technology. And I think, sometimes when I think about what synthetic biology is, I think about it as biotech 2.0. And what's really happened in the past, 2 decades, or even the last 10 years very specifically, is that there have been some enablements from a technology perspective, right? So very specifically, the cost of DNA sequencing has plummeted as well as the cost of DNA synthesis. So in the past decade, now we're able to, acquire a whole lot of genomic information, right? DNA code, effectively. And we're able to build with DNA on a scale that we just haven't been able to before. And so it's still sort of biotech, but now the application space is enormous because of these other technology enablements that have happened in the past decades.
Yeah, I think, people who are familiar with ARC's research, I think are a little bit more exposed to the cost decline work that we've done. And frankly, that really exists like pretty unanimously in terms of, like read and write, right? So sequencing and then writing information back out. But it's really the combination of those two things that gives rise to this kind of, not a cottage industry, but kind of, living on top of those other technology platforms. And, I think one of the things that was interesting for me when I was sort of first learning this is I think it's not quite right to think about it like computer code in the sense that, we have total mastery over it because we invented it, like with, digital computing, right? Versus biology is so unimaginably complex that it's more like us trying to brute force our way in increasingly elegant fashion, an understanding of, and, the ability to like augment and manipulate and bend biology to our will. And I know that your studies, I think when you were doing your doctoral work, you had written about and published on kind of high throughput methods, and we'll get into that in a second. But maybe I think it would be good to just sort of draw a dotted line for people around why it's important to be able to do things at such massive scale. Massive parallelization, for instance, is one of the ways that we got DNA sequencing to become so cheap, right? So maybe thinking about that, but in the context of synthetic biology, would be interesting to learn about.
Yeah, so with our ability to read and write DNA, the things that we can do have sort of exponentially increased, and I think a big focus within sort of the entire field of biotech 2.0 or synthetic biology, there's a lot of mining, right? So we still don't know 99% of biology, right? Some of the most basic questions about what is life remain unanswered. But we're now sort of in an era where we can sequence, enormous amounts of information. We can write this DNA and we can start to explore, a really massive space that we haven't been able to do, right? And we're sort of witnessing this with, companies that are working on gene editing solutions, right? CRISPR, right? There's a lot of focus on, after the first CRISPR Cas protein, Cas9, was discovered, right, we've since witnessed, dozens, if not hundreds, of new CRISPR proteins, right? And we wouldn't have been able to do that unless we had an enormous amount of DNA sequencing information to pull from and the ability to create, right, to write all of these DNA sequences to understand the biology of what's happening.
I think for maybe people who are familiar with SynBio are certainly familiar with this DBTL, this design, build, test, and learn cycle, which underlies a lot of things that happen in the life science industry. But maybe for those who don't know, it's our ability to kind of have a hypothesis and test it in a very increasingly automated and high throughput fashion, right? So to be able to make an educated guess, test it, see how it works, learn from your mistakes or from your successes, and then recycle that very, very, very quickly. But I'm interested again, like flashing back to your doctoral work. One of the things that I came across that I was interested to ask you about, because I know the same technology is used, currently in what you do at Stemloop, is Aptamer technology. And so, before we get into some of the software work that you did at the beginning there, I wanted to just help give people a reference frame for what an Aptamer actually is and why it's useful. And then we can get into like how to design it and actually use it in a commercial setting.
Yeah, absolutely. So an aptamer is a single-stranded nucleic acid. So that could be a DNA or an RNA that's capable of binding to a molecular target, right? That can be a protein, that can be a metal, with really high sensitivity and potentially really high specificity as well. So an equivalent of this are, we have proteins that are called antibodies that are able to bind to specific targets again, with high sensitivity and with high specificity. So aptamers are kind of like the nucleic acid, again, DNA or RNA, equivalent of an antibody.
I see. So, I think it's interesting because people like oftentimes I think when we hear about DNA sequence, it's easy to kind of picture in the abstract like a linear set of letters, right? And visualize it that way. But to your point, these things are not just like abstract linear constructs. They have three-dimensional shape, right? Like the chemical properties of each individual, the A's, T's, G's, and C's, or, in the case of RNAu, they can kink and bend and create these more complex, like lock and key type, fits. And I think that's sort of what you're getting at is like you can design the sequence, but then, you expose that sequence to physics in 3D space, and it just, finds its optimal solution and kinks up together. And then that's what you use to like find and smack onto a target. Is that roughly right?
Yeah, absolutely. So I think people are more familiar with this for proteins, right? So proteins are a linear polymer, right? They're made of individual amino acids that sort of form a chain. But it's not like a piece of uncooked spaghetti where it's just a straight line, right? As you said, physics happens, and this polymer sort of folds up into three-dimensional shape. It might form like a glob or something like that. RNA is the same way, right? As a linear polymer composed of ribonucleotides, so A, C, G, and U, that again folds into three-dimensional space. And the structure that it ultimately forms in 3D space determines its function. This also happens with DNA, right? So when we think about DNA, we're thinking typically of a helix. Well, that helix is actually double stranded, where each strand has perfect complementarity. So it's like, the hooks and the loops of Velcro, where they just naturally just sort of come together and sort of zip right up. But if you only have one of those strands, right, it doesn't have, if it's just the hooks, right, it's not going to be a straight line. It's not going to be a double helix. It's going to be something in between. It might sort of clump up into a ball. And again, depending on what that structure is, based on sort of the physics of the environment, it might have a function, right? Being able to bind to something.
Yeah, and just to get people, I think you've made pretty clear like this linkage between designing that primary sequence and getting a specific three-dimensional shape, but the mapping between those two things is extremely complex and is like it's not something that you can just brute force compute. Like when you really think about it, like imagine each individual piece is acting on all the other ones in superposition, depending on how far they are away or what are the constituent atoms. And it's really like, I think some people might be familiar with this from what had just happened a couple, I think last year with AlphaFold for proteins, right? This step function advance, not perfect, but, really improving our ability to like take sequence information, put it into an algorithm and get sort of structural information, which is a kind of a crude way of thinking about it, but it is a really like Herculean task to be able to do this.
Yeah, absolutely. And I think with proteins, we're starting to solve some of these problems with the AlphaFold. And that's in large part because we have really large data sets that we can draw from, right? So in the case of proteins, these are X-ray crystal structures or other sorts of, electron microscopy based structures where we know how these things look like. We sort of have a snapshot of what these things look like in three-dimensional space, and we can tie that to sequence. And once we have enough of that data set, that's of course when we can start to apply learning techniques and start to sort of predict de novo how a sequence of amino acids might fold into a functional or maybe even a non-functional protein. We still have a long way to go with I think RNA. So we have a good understanding of what an RNA structure might look like if it's mapped in two dimensions, right? But the reality is that there's, of course, that third dimension. And there's still, there's a lot of progress that's being made here, but still much more progress left to be made.
At the risk of sending us into a death spiral, also 4D, right? Like some of these things change as a function of time and their environment, which, it's always simple with biology. So that's good. I wanted to maybe just build off of the conversation on Aptamers to talk about, one, I'm really interested to learn a little bit more about this open source toolkit that you developed called FASTAptameR, which I understand is still, propagating and being used quite often. And then, secondly, just the bridge to this original kind of foundational work that you did, and making the link or the bridge to what Stemloop does is all about, fluorescence and sensing, and like, how do you get some of these abstract things that we're talking about to be like tangible and visible for people. So those two things, if you could kind of help, fill us in on that, I'd love to hear.
Yeah, absolutely. So with aptamers, there are natural aptamers, right? So there are natural RNAs that are known as riboswitches that, again, fold in three-dimensional space and can bind to a particular target, and they can control gene expression. But there's also a really enormous class of aptamers that are evolved in the laboratory. And a big portion of my graduate work was around evolving aptamers that can bind to viral targets. In our case, the target that we were really interested in was HIV reverse transcriptase. And we had an RNA that we knew could bind really tightly to one specific reverse transcriptase. But we had this question about, what if we could create an aptamer that could bind to and inhibit, right, an entire family or an entire class of
Hmm.
this viral protein, right? Because that would obviously have some utility for therapeutic applications. And so the way the work that has been done traditionally in the past is you go through this process of evolution, and then you're basically starting with these massive libraries that can be, 10 to the 15 sequences at the very beginning, and you sort of whittle that down through a laboratory evolutionary process. But at the end of that process, you still might have millions, billions, or trillions of different sequences. And traditionally, what people have done in the past is known as Sanger sequencing, which is really low throughput, and you might get maybe a few dozen sequences from that process. Well, with the advent of next generation sequencing technologies, from about 2010 onwards, people in this field started to increasingly use next generation sequencing. And I was starting to use next generation sequencing as part of my work. But the problem that we ran into was there wasn't any software that we could use to analyze the outcomes of the process that we had just followed, right? So we'd get sort of a data dump, and we'd have to figure out, how do we process, hundreds of gigabytes of information to have anything, sort of useful come out of that process. And so, it was born out of a problem that I faced. We created a really sort of easy to use open source toolkit without any external dependencies. We published that back in 2015. It's been used, throughout the community. We actually just posted a preprint for, FASTAptameR 2.0, where we've added a graphical user interface. There's a web-based server. Again, right, trying to lower the barriers for the use of next generation sequencing for the selection or the identification of aptamer sequences.
It's a really important thing that you mentioned too about, sometimes I like to take a step back, especially when talking about something like sequencing, and try to get people to understand that sequencing is not like a plug and play tool that exists in a vacuum, right? There is an entire workflow or pipeline all the way from, like in a clinical setting, getting a sample, preserving it, fixing it, literally shipping it in a cold chain. All of these things are opportunities for error and variability to sneak into the system and make the overall process less efficient or effective. And so to your point, the advent of sequencing was amazing in terms of like lowering the barriers to generating data, but it just shifted the problem downstream a little bit, because now it's like, making sense of it all. I mean, this is exactly what like a lot of clinical diagnostic companies, have to deal with, because, to your point, it's like, how much of the genome right now is operationalized and actually clinically, has clinical utility? It's like not that much still. I mean, we just finished sequencing it last year, so I guess. So you've talked about, kind of the software toolkit, but then you also started combining these RNA aptamers with fluorescent molecules too, right?
Yeah, that's right. So there was sort of a class of aptamers that are known as like fluorescence activating RNAs, And so these are RNAs that are single-stranded and they can bind to a dye. Now, that dye normally is not fluorescent in solution, but when it becomes bound by this RNA, it almost gets pancaked within this RNA structure. And then if you hit it with the appropriate wavelength of light, it gets energized. And the only way for the dye and for that RNA to get rid of that energy is through sort of a fluorescence pathway. And this was really interesting, right? Because people have had these fluorescent tools for proteins for a really long time, right? So there are things like green fluorescent proteins that revolutionized how we were able to study biology, right? It sort of enabled us to look at where a protein might be in a cell or where it's trafficked in a cell or even outside of a cell. But we didn't have those same tools for studying RNAs. And these fluorescence activating RNA aptamers started to appear about a decade ago. I got really excited about, how can we use this to monitor or track the formation of RNA within a cell? Or how can we use this as a way of studying transport of an RNA from outside of the cell or into this inside of the cell? So that sort of led to, I think, a lot of the work that I did as a postdoctoral fellow as well. And, sort of the sensing technologies that we built really relied on this insight that we had that we could use an RNA molecule to create fluorescence as a visible, measurable output without having to rely on a protein to do the same thing.
Yeah, it's a good point that you made about I go back to this whole like form is function and GFP, the green fluorescent protein that you mentioned. I don't know if it's the same principle like the pancake versus like I believe the structure of green fluorescent protein is almost like this barrel where the fluorescent molecule is kind of trapped in the middle. And the reason why it works and has evolved this way is the protein is literally, it's shielding that fluorescent molecule from being quenched by whatever aqueous or water solution is around it. So it's, again, like it's an example of like form and function are the same thing at the micro scale in biology. And so what you're saying is you figured out a way to combine all the work that you've done with Aptamer technology, not having to use proteins, and still you have what is essentially like a reporter or a marker that something is happening, which you can use to kind of like give you information back out about, were we successful? Did something work? Because you have, indication that it did or did not. Is that fair?
Yeah, absolutely. So the mechanisms are different for an RNA fluorescent reporter versus something like the green fluorescent proteins. But you're absolutely right. So we were doing a lot of work engineering these RNAs that can bind and fluoresce as a way of being able to report on something that's happening inside of a cell.
Got it. So maybe take us to your postdoc work and maybe early indications of what you wanted to apply this technology to. Right, I'm thinking about you back in the baby gate again. Right, it's not just that you have the bench next to the laundry room, but we got to apply it somehow. So what were your first inklings of like I have this tech, I know what I want to do, and here you are able to kind of like bring it out into the world and do something.
Yeah, so I think the one insight that we had was we could create an RNA that we could very easily observe its fluorescence, right? And traditionally, people that have built sensors in the field of synthetic biology, they would really rely on this protein component, right? Green fluorescent protein. But to produce green fluorescent protein, you need to go through the process first of DNA transcription. So taking a DNA, making an RNA, and then going from that RNA to a protein through a process called translation, right? Just to get this visible fluorescent reporter, right? GFP in this case. The insight that we had was actually, if we're using an RNA that is by itself functional, fluorescent, and visible, then we can just skip that second step of translating that RNA to a protein, right? And some of the advantages that would allow was, for one, we'd be removing complexity from the system, right? So biology is really complex, and the more we can sort of disentangle all of this complexity, the better off that we are, right, for a robust, engineerable, and sort of a predictable system. The other thing that happens, though, when you get rid of that second step of translation is you save a lot of time and resources. So if you're making a protein like green fluorescent protein, you not only have to, make the protein, but then you have to actually wait for that protein to mature before the fluorescence can actually be observed. So when I started my postdoctoral work, we had this sort of idea of, hey, what if we could just use the process of transcription, right, going from DNA to RNA, to create an entirely new class of sensors. I think what was also unique about what we were doing is, people in the life sciences have focused in large part on applying, advances in synthetic biology very specifically towards human health and diagnostics, right? Therapeutics and diagnostics, the standard sort of biotech. Our approach was, well, there's a lot more than just human therapeutics and human diagnostics that are important, right? What if we could measure whether a plant virus is at risk of decimating an entire crop of bananas or oranges, right? Why don't we use the tools of synthetic biology to make that easier, right? To diagnose whether or not there's a problem in the field. We were also thinking about the environment. We were very specifically thinking about water quality monitoring, right? This is a really big problem globally. And if you look at any reasonable projection of the future, water quality issues are at the very top of the list. And so we were thinking about how can we use the tools of synthetic biology? How can we use things like this fluorescent RNA to create sensors to sort of solve these challenges that other folks had largely been ignoring?
Right. And two, I imagine like as you're going through that process, like the product market fit begins to kind of just manifest in front of you. And what I mean by that is, and I'll use your example of like, more human-centric diagnostics and therapeutics. We typically rely on very centralized, expensive analytical equipment to do these things. And that might be fine for those applications. But in the situation where, especially in low resource settings where it might be really important to take in the field measurements, you have to be able to free yourself up from, expensive, delicate, fragile machinery. But also like the I think the other really interesting thing is, you're not just looking at like biological contaminants, for example, like with water quality. I know you guys do a lot of work with lead or with other sort of like metal, contaminants. And so when you think about what are the other like decentralized sensing platforms, it's like, well, we've already talked about CRISPR. You can use that, but that's a little bit more limited in terms of what it can snap onto and detect. And then, same thing with like Oxford Nanopore and the more handheld DNA sequencers are fantastic, but that again narrows you to DNA, RNA, and then maybe someday proteins, but not these metallic or other contaminants. So you have not only do you have a biosensor that is robust in the field, but it also has like a wider funnel maybe at the inlet for what it can detect.
Yeah, absolutely. So, there's been a lot of really great progress with CRISPR-based diagnostics in, I want to say about the last 5 years. And, I think a lot of our work is sort of inspired by what's happened in this space, right? This idea that we can decentralize or democratize how we test for things like the coronavirus or the flu virus using some of these CRISPR-based diagnostic methods. But to your point, right, CRISPR is a really great system for sort of searching and finding a sequence of DNA or RNA, but it's not really capable of being able to detect a metabolite or a toxin or a heavy metal, right? And these are all things that are, of course, really important to detect. And we've created a technology platform that allows us to broadly be able to detect all of these other things that are really important. And I do want to touch on one other thing that you said about sort of like analytical testing, right? So analytical testing, right, doing chemistry sort of in a centralized laboratory setting is really great for a number of applications. And we don't intend to sort of disrupt or even replace that. But the facts with analytical testing in a laboratory are that it's costly, it's complicated, and it's slow, right? And because of those characteristics, it inherently does not scale well, right? And so 2.5 years ago, when I was sort of pitching Stemloop, I would tell people that laboratory testing doesn't scale. And I think they sort of understood that superficially, but they didn't necessarily empathize with it deeply, right? And fast forward, now that we've lived through the COVID pandemic, and maybe we've been in those situations where we had to go get a test and it was impossible to find an appointment time. And even if we found an appointment time, it might take 2 weeks in some cases to get our test results back. Well, what's the value of that test now? It's no longer important if you get it 2 weeks later and your body has cleared itself of the virus, or maybe now you're in a hospital bed somewhere. And so, I think that's sort of core to the problem that we want to solve, is that analytical chemistry and lab testing can't scale, but biology has already created, a lot of these really elegant sensors to detect metals, toxins, nutrients, pesticides, whatever it may be, and democratize and decentralize how we test for those things in our environments.
Yeah, it's a really good point that you made. And I want to make sure people take away the fact that like turnaround time is utility. And it not just in an infectious disease scenario, but so many different scenarios. I mean, I'm sure we're going to talk about it with water contamination, but time to result is everything. And so it's really, really important. It's speedy, and also doesn't necessarily rely on trained users as well, which are also difficult to scale and expensive. Labor is extremely expensive, especially in like you mentioned, the analytical kind of central lab setting. So maybe just thinking about kind of a high level bird's eye view of what Stemloop's kind of tangible product looks and feels like, for people that again like are trying to kind of get their minds around like something that we're talking about in the abstract, right? It's a and I'll let you explain it, but the way that I've sort of bucketed the parts of the technology, right? You have an input layer where you can kind of codify like what set of, we call them analytes, but what set of things that you're looking for, whether it's like a heavy metal pollutant, for example, like you mentioned. And then you have the place that I really want to spend some time is talking about logic and the middle layer of translating, biomechanically or what have you, that input information and making decisions about it. And then we've also already talked about the output, which, the fluorescence, the light, right? So you have input and output, but this mysterious middle layer, I think is so fascinating about what you do.
Yeah, absolutely. So, when we think about computers or we think about electronics, right, we're thinking about an input, we're thinking about information processing, we're thinking about an output, right? And that could be, a GIF of a cat on your web browser, right? Could be your output. If we think about how biology does this, right, biology's operating system is what's known within the field as the central dogma, this process of gene expression. DNA gets transcribed to RNA, RNA gets translated to protein, right? This is how biology computes. If a microorganism is in an environment where all of a sudden there's a whole bunch of heavy metal toxins in that environment, it's capable of sensing that change in the environment and responding. And the way it does this sort of sense and response function is by turning genes on or off. And what we do at Stemloop is really harness that central dogma, right? And we run what are called CellFree Systems. And another way of thinking about this is like this is a gene expression system, right? So these are all biomolecules. They're sort of like clear liquid at the bottom of a tube, and you can freeze dry it so that it's shelf stable and it can be now distributed without sort of cold chain requirements. And in the case of water quality, all you have to do is add a drop of the sample that you're interested in to the reaction that then rehydrates, it fires up this gene expression machinery. And if the analyte, the contaminant that you're interested in detecting is present, then that engine runs and it produces the output, which again, it could be something like a fluorescent RNA, or it could be other sorts of reporter molecules that are visible to the eye. So one of the things that we've done, I think we're all sort of familiar with the at-home COVID test, right? Which were kind of a game changer in how we, respond to the pandemic. Again, by sort of taking the testing, the sensing and detection outside of a laboratory and being able to do it, in your home or at your workplace. Very similarly, we can take our cell-free system and put it on that same format, right? It's a lateral flow format. This is what most of the at-home COVID tests look like. This is what pregnancy tests, have looked like for a very long time. So we can very simply set up a reaction where, the test is basically run on this lateral flow test or a lateral flow strip, right? You get one band to tell you that the test is working, and that second band only pops up if that analyte that you're interested in detecting is present.
Mm-hmm. Yeah, and the cell-free aspect of this, like again, I don't know if people will necessarily appreciate, but I think it's really important to highlight how important a cell-free system is. I mean, when you brought up the first example of a little, let's say a microorganism like a bacteria swimming around in a tube and responding to its environment, that's a single cellular organism that is not impervious to big swings in the environment, right? So if you imagine like shipping this to another country for use, right? Changes in pressure, changes in heat, even physical like shaking could be something that kills the cell or ruptures its membrane and then exposes all the inner good stuff to the hazards of the environment and totally destroy or disrupt the whole system. So what you're saying is you have engineered these cell-free biomolecules to be robust and stable, not living within the confines of an organism like a bacteria, right? It's just this homogeneous mixture inside of a tube that, to your point, you can freeze dry and ship.
Yeah, that's right. So, in addition to, all of the changes, the really drastic changes that a cell might face in the environment, at the end of the day, a biological cell will experience evolution, right? It's going to replicate, it's going to divide, and it's going to grow. And we might try to program a microorganism to do something, but evolution has its own course, right? And that might run counter to what we're trying to engineer an organism to do. So our approach, and we call this, cell free, is basically rather than using the microbial cell, we want to use the components, the biomolecules from that cell to create a sensor, right? So again, this is like the gene expression engine. This is minimally that process of transcription, and it might be translation that we're capable of sort of, doing the biochemistry in a tube. And there are a lot of advantages, right? So you mentioned lyophilization, freeze drying it, right? So I think the good analogy here is like astronaut ice cream, right? It's sort of dehydrated. All of the water has been removed, and now it's shelf stable, and you don't have to worry about refrigeration. We can do the same thing with a cell-free system. That's a lot harder to do with a biological cell. But with a cell-free system, we also, now that we've gotten rid of the biological membrane, we don't have to worry about transporting the analyte that we want to detect across from the environment into the cell, right? We also don't have to worry about, this is really a practical thing. If we're producing a batch of cell-free biosensors here in Chicago where we're based, and we have a customer that's in the European Union, let's say they're in Frankfurt, we don't have to worry about sending a genetically modified organism, right? And having to worry about, regulatory concerns around import or export around GM and GMO products. We also don't have to worry about accidental release. So there are people that have programmed biological cells to be sensors, right? And we do very similar things, but in a cell-free approach where we don't actually require that cell. If you're using a cell, you have to worry about, well, what if my sensor accidentally gets out into the environment where it's potentially capable of replicating, and it might even, potentially disrupt an ecosystem or something like that. So our cell-free approach has a lot of advantages, but those are just some of them.
So I wanted to dig in a little bit deeper to the actual inner workings and the mechanisms that let you translate an input or even a series of inputs to an output, or maybe even a different flavor or type of output. I think the people who might be coming from more like classical computing, or even if you've just been, loosely exposed to it, people might be familiar with like what are the most basic, simple, fundamental units of logic, right? Especially when used in like computational or in software, right? So you have things like and, right, or, right? So and might be a situation where some people might know this as like Boolean logic, where you have things coming in and you say, well, if A is true and if B is true, then push the output forward, right? And then or could be one or the other, but not both or not neither, right? And when you stack these things together and have them speak to each other in layers, you end up being able to construct like more sophisticated or more complex logical computations. And so again, like I think this is a beautiful example of taking something that is like totally ethereal and abstract and thinking about everything we've talked about thus far about form and function, and these are real physical molecules that are talking to each other. How did you think about those computational ideas and actually cause them to be manifest in physical, tangible 3D space?
So there's a lot of work that's been done around building genetic circuits that allow us to implement Boolean logic, things like an AND gate or an OR gate. I think we've been inspired by a lot of what other people have done to implement genetic circuits inside of a living organism, and we just implement them outside of these organisms in these cell-free biosensor reactions. An example of why this might be useful, and I think I should step back and say that biology does this all the time, right? Biology is computing, hey, is this environment too hot? Is this too cold, right? Should I move from, where it's 90 degrees outside into this air conditioned building, right? And biology is, taking a lot of different inputs, right? So it might be not only temperature, it might be pressure, it might be nutrient availability, it might be toxins in the environment. And these organisms are processing this information in real time to make decisions. And we do very similar things here. Happy to sort of dive into the details, but an example of this is we might have a sensor that responds to not only the presence of the heavy metal lead, but maybe it also responds to the presence of zinc, right? And if we're building a lead sensor, we don't want that sensor to light up if zinc is present, right? And so what we do is we create these genetic circuits that can perform that logical operation to where the sensor only lights up if it's zinc, or rather lead, and not zinc.
I see. So physically, I mean, and I know enzymes and things do this like quite often where they bind to their ligands and they fit together like lock and key, but there might be, I think something that people might be familiar with is typically when you have that the combination of molecules binding, there might be like a conformational shift or a structural, the molecule literally changes shape because it's been contacted and binds to something else. So is that sort of what you're talking about, like engineering these things to be like, well, if you bind to one thing, don't change that much, but if you bind to two, then it's going to flip on and carry the message forward.
Yeah, so this is, I think, one of those things where like visuals help a lot, right? But one way to think about these sensors is, let's say you have a piece of DNA, right? And let's say that piece of DNA is like a pen, right? Our sensor might be a protein, and it's a protein. We can think about this as like a hand that binds onto that pen. And this might be sort of the default state, that the sensor, the hand, is holding on to this pen and it's just not letting go, right? But when an analyte is sensed, and let's say it's, the heavy metal lead, that hand might let go of that pen. And now this pen is now free to be able to do other things like, for writing or for drawing, etc. So that's kind of, I'm trying to use the simplest analogy possible here. I'm not sure if that entirely works here, but we have these protein biosensors that bind to a piece of DNA, and they either bind or unbind as a function of whether or not the analyte that we're interested in detecting is present. And when it's unbound, we can do the process of transcription, right? It's sort of, there's no more roadblock that's there. Whereas when it's bound, it's off. It's kind of like the gate is closed or the gate is open. And when the gate is open, you allow that information to flow through.
So I know that the technology platform has gone through a couple different incarnations, and I know that you've expanded upon it, made it more robust, and now you're at a point where Stemloop is and I'll let you feel free to kind of take the reins and talk about the conversations you're having with investors and with customers, but you're at a point now where I think it's fair to say you're at minimum viable product. You're ready to sort of like get this stuff out into the world, and I wanted to know if you could kind of explain how you winnowed down the application space and focused on one particular thing to focus on first, and then how you made that calculus and sort of where you are in the timeline of getting that to market.
Yeah, absolutely. So, in terms of how we sort of winnowed down the application space, the simple answer is, we got out of the building, right? And we talked to as many people that we could. So, we started with a hypothesis, actually, two sort of hypotheses, one in industrial biotechnology and one in the water quality monitoring market. For water quality monitoring, we're very much focused on our first, MVP for the detection of lead in drinking water. And this is after ruling out a lot of other contaminants or analytes that people are interested in, right? So fluoride and arsenic, these are really important to measure in water globally, but the market size and everything else that we sort of uncovered doing customer discovery indicated to us that like this is a market that we could potentially tap into, but maybe it's not a good beachhead market because the sales cycle is too long, or the size of the opportunity is not lucrative enough for us to justify it. With lead, it was the complete opposite, right? There was sort of this burning demand from the folks that we were talking to have better tools, right? So we have a really large problem that we have to solve in this country around lead in our drinking water. It's, in fact, kind of everywhere. It's baked into our infrastructure that we have lead pipes. The only way that we're going to solve this problem, and it's now a national priority to solve it, is if we know when and where these problems exist. And so the only way to do that right now is with analytical chemistry in a lab. And going back to earlier in the conversation, if you were to send a sample of drinking water from your home, right, the best approach for you to take is you collect bottles of water, you ship it off to a laboratory. You might be paying hundreds of dollars and waiting weeks, if not months in some cases, to get your results back. And I think, as we've already described, like that's not super useful, right? And so we're really focused on being able to not only provide rapid answers, but to do so in a way that can scale so that we can collect 100,000 data points, a million, 10 million, 100 million data points easily and effectively to inform decision making.
Yeah, and I mean, let's not lose sight of the fact that like shipping water is expensive because it's heavy and bulky.
That's right, and that's actually like an underappreciated fact, right? I think like a gallon of water is like 8 pounds or something like that. It's quite heavy.
Yeah. So what are some of the early conversations that you've had? Like, who are your first users? I mean, I imagine, there's obviously going to be like some federal push to doing this. I don't know if there's a changing landscape in terms of how you mentioned it's a priority. I don't know if that means that the funding landscape has evolved. I'm also not totally aware of like, is the current water quality, is it like an oligarchy where you have just a bunch of people like analytical labs that dominate it? Like how do you actually move from where you are now with the product to actually having it distributed and used in a way that maybe an entity can be, I mean, obviously, like you're saying, you want to have sensing everywhere, you want it to be ubiquitous, but you also want it to be sending and beaming information back to a source where you can actually run analytics at like a meaningful scale. So how does that happen?
Yeah, absolutely. So, the current paradigm, if we think about environmental testing, right, and so that includes, air quality, that includes water quality as well. It's not an oligarchy. It's actually hyper fragmented. So you have a lot of regional laboratories within a city, within a state. You do have some, multinational corporations that have sort of a global presence, and they might run labs in a lot of different geographies. But by and large, this is a fragmented process, right? Our approach here, and we're talking, for our MVP product, we're talking to engineering contractors that are working on some of these infrastructure problems. We're of course talking to drinking water systems that have a legal obligation under the EPA's lead and copper rule to solve these issues. We're also talking to folks in the water filtration space, right? So companies that offer pitcher filters or faucet filters to remove contaminants like lead obviously have a clear desire to convince people, to make people aware of the fact that there's lead in their drinking water, and that the products that they sell provide a solution to removing lead in their drinking water. And we're having early conversations with these folks, entering into some pilots later on this summer. But the way that we're thinking about this is these are really inexpensive, really easy to use devices that can be mailed to a household, right? So we can blanket a city, we can potentially collect 100,000 data points, and a user would basically just snap a picture of the result. That would, of course, go to the cloud, to a database, where we can then aggregate all of this information to get that high level bird's eye view of where is this problem most prominent. And that's where we direct our resources to solving the problems then.
So just in the interest of time, I wanted to end things by asking, I think about the fact that our audience is pretty diverse. We might have some people who are interested in just learning and keeping tabs on you and Stemloop and seeing how things go. But we also might have, potentially interested investors or even people who might want to join the team. So kind of where are we in those relative phases, and how do people, keep themselves posted or maybe even reach out to you and the team?
Yeah, absolutely. So our website is stemloop.com. That's all one word, STEMLOOP.com. I think we're pretty active on both Twitter and LinkedIn. So I think those are the best sort of like social channels to connect with us at. We are both fundraising and hiring. So if you're a scientist that's super interested in what we're doing, we are looking for a scientist, at least one, if not two, that we're going to be hiring this summer. And fundraising, so we've largely bootstrapped Stemloop to date on government grants and contracts. There's, of course, interest from the National Science Foundation, National Institutes of Health, the Department of Energy, and Department of Defense for a lot of different reasons. And we've bootstrapped our company so far using that support. But we have started to raise our seed round, and we have, $1 million commitment. We're working to raise another $2 million on top of that. So if folks are interested, it's my first name at stemloop.com. Feel free to reach out directly or connect with us through social, and we'd be happy to connect and chat more.
Perfect. Well, thank you for sitting down and spending so much time with us today. I know I learned a lot, and we'll be sure to have everything hyperlinked for people to go and follow you. So appreciate your time.
Well, thank you so much, Simon, for having me. Every time we talk, you ask some really great questions. So it's been a pleasure to chat today.
ARC believes that the information presented is accurate and was obtained from sources that ARC believes to be reliable. However, ARC does not guarantee the accuracy or completeness of any information, and such information may be subject to change without notice from ARC. Historical results are not indications of future results. Certain of the statements contained in this podcast may be statements of future expectations and other forward-looking statements that are based on ARC's current views and assumptions, and involve known and unknown risks and uncertainties that could cause actual results, performance, or events to differ materially from those expressed or implied in such statements.